let's start. So today we're going to finish the x86-64 ISA. So the point of having this separate ISA is that we want to actually have a small subset of x86-64, which is simple enough to implement in hardware and complex enough to make some interesting programs. Okay, so original x86-2 like such a big ISA and very complex. And it's very difficult. We won't be able to finish, implementing this one in hardware in single term. So we actually have a small subset of instructions, that actually captures the many, interesting details of a hardware design. But also it allows us to write interesting program. So if you remember, we actually have like 15 registers here. Originally Intel's x86-64 actually has 16, but we actually have one fewer registers. We have 15 registers, so it requires 4-bit ID for register specifier. And the last special, it's like 4 bits, so it's 0 through F, right? 1, 1, 0, 0, 0, 0 through F, 1, 1, 1, 1, so it's 0 through F. And the last one, this F register is used for special purpose. This one actually indicates no register. It's like empty, not used. And we actually, looked at a few, instructions last time. Here the add instruction, for example, this add instruction actually takes 2 register operands, like a source and destination. And if you assemble this instruction, it will actually be translated into 2-byte machine code. And the first machine code is 6260. This one is called opcode, by the way. So opcode specifies what kind of instruction it is. Okay, so if you actually parse, if you decode this opcode, this one is like actually add instruction, and then it actually allows you to understand the layout for the following subsequent bytes. So if it's 60, we know that this one is add Q instruction, so it actually requires 2 register operands, RA and RB. So in the next byte actually specifies 2 registers. So in specific example, if add Q RAX RSI, then it adds the value of RAX to RSI and store the result back to the RSI register. And this one actually the register 0, register number 0, and this one is register number 6. So it'll be encoded as 6006. So maybe we can make a question like this. We actually may give you few bytes, and then what disassembled instruction, meaning that you actually reconstruct the assembly instruction from this machine code, or vice versa. Maybe you can give you some assembly instruction and ask you to translate into a encoding, like byte encoding. You can expand it to different instructions, like add, sub, and XOR. They only differ in opcode because they actually have the same format. They actually all take a 2 register operands, source and destination. And they only differ in opcode, so that if it's 60, it's add, 61, sub Q, 62, and 63 XOR, right? So only they differ in opcode, otherwise they are the same. By the way, the second like a nibble, second 4 bits, is called a function code, because 6 is kind of, 6, the first 6 indicates that this one will be so-called ALU instruction. ALU is arithmetic logical unit, so it's 6, it's the ALU instruction, and then the second one is actually function code, 0 through 3. And let's move on to move instruction. So in our original x86-64, move can take very complex addressing mode, right? If you remember, in most generic form, we actually had a scaled mode. We actually had 4 specifiers for addressing, a D, 2 registers followed by scaling factor, which is very complex addressing mode. But in our y86-64, we only have 4 different types of move instruction, and we actually have a prefix RR, IR, RM, MR to specify the addressing mode for both source and destination. Because in move instruction, we actually copy the value from the source to destination, right? So this is RR move is actually is like a register to register move. So in this case, we copy the value of register A to register B. Second one is IR move, like immediate to register move. So we actually copy like constant, like immediate value to register B in this case. So this one is an example of like using no register, right? Because we actually, in this case, in case of IR move, we actually use like 10 bytes. So this one's byte 1, this one's byte 2, and this like a V field actually takes 8 bytes. This is B3 through B10, right? 8 bytes. So it will be, so in this case, we copy the value of V to register B, and we are not using this like a register field, because we only need like one register in this case, right? So the second register field is kind of unused. So in this case, this one is fixed to value F, or 1111 in 4 bytes, 4 bits. The RM move is register to memory move. Copy the value of register to memory location. This one is, by the way, what's the register? What is this instruction called in general? Register to memory move. Store. You remember that? This is like a store instruction in general. Store instruction is basically copying the value of register to memory. And this one is the opposite. This is load instruction. Load is basically copying a value in memory into register. Okay? This is in general, although in x86-64 we only have like a one instruction move, which actually covers all different like a variety of moving value around. But in other architectures, they actually have designated load and store instruction to access memory, accelerate memory. Okay. So this is a RM move is a register to memory move, which is store instruction. MR move is memory to register move, which is a load instruction. Okay, and as I said, we only when we access memory, we do not support all the addressing modes supported by x86-64. We only have very simple displacement mode. So in this case, we only take like one register and one constant value. That's it. But in more general form, if you remember, we actually something like in the original x86-64, we supported more complex addressing, something like 8 plus, RSI, RDI, 4, or something like that, right? That's kind of more like a general form, which is not supported in x86-64 because it's too common. So it's kind of design choice. And if you want to do this kind of like support this kind of addressing mode, you can emulate it. So emulation. You can emulate it in software because you can actually do the same thing using multiple instructions. Okay, so you can actually emulate it in software instead of like doing natively in hardware. Okay. So here are some examples, move instructions like x86 versus y86. So x86, we only have like a move instruction, but automatically the CPU will automatically know based on the operand types. It's like a memory to register or register memory. It'll be inferred by the hardware itself. But in this case, we actually have specific like a prefix to show that where the source operand comes from, where the destination operand goes to. So in IR move, we actually takes this like a constant immediate value and store the result to the IRDX register. And in this case, according to our, according to the previous slide, the IR move actually has opcode of 30, and these two are like register specifier. So this case, right? Actually, this one should be, I think. To be precise, this one must be F, but it doesn't really matter because this register field is unused anyway. If it's like IR move instruction, we only need one register operand, right? And that register operand is specified in the second like LSB of the second byte. The second the second like a lower lower nibble of the second byte. So this 8, this nibble is not used anyway. So it can be any value. But generally, our convention is we actually put F here instead of 2. But even if you put 8, it's kind of harmless. It's fine, as long as we actually have the correct specifier for the second nibble. Okay, and this like a constant ABCD value is actually encoded in this like brief build. So this instruction actually takes like a 10 byte, as I said. Okay, so what about second instruction? So second instruction is RR, register to register move. So we only need to specify 2 registers, the source and destination. And this one is the source, and this one is destination. So 20 means that it's register, register move, and we actually have 2 registers, RSP and RBX, which are register number 4 and 3. Okay, so and so on. So it's the same thing. It's just MR, memory to register, and register to memory. This part encode -12 in this example because this one is where this constant displacement goes, and in the second case, again, this value is encoded here. And then note that, this because this Intel architecture is little endian architecture, if you remember. So the little endian architecture means that the LSB, if you have like a constant value, the least significant byte actually goes to lowest address, right? Because we assume the address actually increased to this direction. So this one is like a lowest address, which actually takes the LSB, the least significant byte of the value. So that's the reason why 1C goes here, 04 goes here, and the remaining bytes become 0. Okay. Conditional move, it's more or less the same. So I mean, we actually already learned this RR move, register to register move, which has opcode of 20. It takes like 2 register operands RA and RB. But we actually, if you actually have like a different, if you actually change the nibble, the second nibble, to different values, then this one becomes the conditional move. So the conditional move takes the same format as register move. And if this like a second nibble becomes non-zero, then that means it's conditional. So if it's 0, it's simply just unconditional, just move regardless of the value of the flags. But if you actually have non-zero value in the second nibble, like a 20 or 21, 22, and so on, and 21, 22, 23, and so on, then actually the move instruction is completed, like executed only if certain condition is satisfied, depending on the value of the nibble. So if it's 21, so it's like a move when less than or equal. So it's like a C conditional move LE. So the value of RA is moved to RB only when the LE condition is satisfied. The value is less than or equal to some value, because it's these flags will be set by the previous instruction as a result of computation. Maybe CMP or test. They actually set the value of the flags, and these instructions will be executed only if a combination of flags become true. And move when less, move when equal, move when not equal, move when greater than or equal, or move greater. Okay, there are some different combinations. So we can actually use this instruction to implement like a short if then else and so on, right? So so it's basically we conditionally copy the value from source to destination register. The next instruction is jump. Jump is also have like this, like it actually has like a 9 bytes. So first byte is opcode. The next 8 bytes are constant values specifying the destination address. Okay. So generally referred to as JXX because depending on this XX, maybe it can become conditional or unconditional. Sorry. So encodings differ only by function code in FN. So if FN is 0, for example, then it's like unconditional, like an unconditional jump. It's like a go-to. And if it's non-zero value, it becomes branch. The branch is, the jump is executed only when a certain condition is satisfied. Otherwise, it simply goes to the next instruction. That's the conditional jump. Also, like one characteristic of this instruction is that we encode full destination address. Basically, if you want to jump to the address like 4000, then actually you put 4000 there. I mean, it's like called absolute addressing. So absolute addressing is simply you plug in the real target address into the instruction. That's called like absolute addressing. But there's like other addressing modes too. Something like one of the popular thing is what is called PC relative addressing. So here, PC relative addressing is, instead of like putting the exact target address into the instruction, you can actually put the delta from the current location. Okay, so the idea of like PC relative addressing is that, here's the observation. When you actually have like a jump and branch, usually the target address is very close to the, usually like nearby. It's not that far off from the current instruction, right? In the case, you can actually save bytes by encode only the delta, like the difference between the current instruction and then target instruction, instead of like putting the absolute like a 64-bit address. So you can actually save more bytes because usually jump target address is pretty close to the current like a branch instruction, jump instruction or branch instruction. So that's called like a PC relative addressing, which is pretty widely used in like all different types of architectures, including x86, 64. So in this case, but to make things simpler, we actually don't support this like PC relative addressing, but we only use absolute addressing. Like just put the real target address in this build. That's the build. So there are like a variant of jump instruction. As I said, all these jump instructions start with 0. And start from like a 7 something, 70, 71, 72. So if 70 is like an unconditional jump. So whenever you hit upon this instruction, you have to actually go to the target address. It's like unconditional, right? And if you actually have like a 71, now these are like all like conditionals. So conditional jump means that you jump to the target only when certain condition is satisfied. Otherwise, you simply move to the next instruction. That's like conditional. Or in some other literatures, some literature calls this one is like a jump or unconditional jump. And this one is also called branches. Right? The reason why it's called branch is that your program control actually diverges, right? If its condition is satisfied, you go to like a remote location. Otherwise, you go to next instruction. So it's kind of point where your program's control diverge, right? So that's the reason why this conditional jump is called branch. But in like unconditional jump, it's not really branch, right? Because you always, whenever you hit upon this instruction, you have to go, right? There's no like a divergence of control. So this one is called, this one is called jump or unconditional jump. And these instructions are called branches because it's a branching pattern, right? Right. So also, y8664 also support like a stack operations because by now, hopefully you understand how this stack and function call works by doing homework number 2. I mean, I hope you have some fun with it. Basically how functions is called, how these arguments are passed around, and so on. So, so stack is region of memory holding program data, especially for like local data. So whenever you declare some function inside, declare some variables inside the function, then that variable is placed in stack, and they will be reclaimed. They will be freed once your function call is finished, right? It's like, it actually has a very limited scope, limited like lifetime, only duration of the function call. So if you remember, we actually have like a push and pop instruction in original x86, right, to support function calls and so on. So if you remember, it's more or less similar to x86 64. So, there's a special register called RSP, like stack pointer, RSP register, that actually points to the top of the stack, right? The top of the stack is the most recently pushed element, right? So, and by convention, the stack grows downward. Downward means, you start from, very high address region, and as you move on, the stack grows downward towards zero, towards like address zero. That's the convention. So, top element, this one, stack top element is placed at the lowest address in the stack. So when you actually do push on a new element, then you must actually first decrement the stack pointer, right? So because the stack pointer actually points to the most least recently pushed element. So you actually have to decrement the stack pointer first to create some room for the new element, right? You have to do that first, and then you actually place your data to the newly created space, like a storage, like a newly created word. And after popping, the stack pointer actually increments back to the original location, right? So that's a push and pop. So if you actually push it, the RSP will be decremented, and if you actually pop it, P will be incremented, right? So that's how this stack grows and shrinks. So there are two instructions, push Q and pop Q. So what does it do? So in push instruction, first, if you execute push instruction, what it does is it first decrement the stack pointer by 8 because we push a register value, like a 64-bit register value. So, and then we store the word from register RA to memory at RSP. Okay, that makes sense. It's like x86 64. That's push, and that's it. So you simply decrement the stack pointer and then store the register value to the memory. That's it. And pop instruction is the opposite. So first you read word from memory at RSP and save the data into register A and increment the RSP register by 8. It's also like the same as x86 64. Okay? Call and return. And call and return, they actually, call actually has opcode of 80. So whenever you hit upon new instruction starting with 80, it's call. And it's followed by 8-byte destination address. So whenever you actually call some new function, whose starting address is specified by this dest field, then you first push the address of next instruction into the stack. So what is this next instruction? What is this address? What is this? 이게 뭐죠? Push the address of next instruction. 왜 다음 인스트럭션의 주소를 왜 스택에다 push 하죠? What is this address? 리턴 어드레스죠. 그죠? 리턴 어드레스죠. 그 펑션의 실행이 끝나면은 복귀해야 되는 그 어드레스 다음 명령, 그러니까 펑션 콜 바로 다음 명령으로 복귀해야 되잖아요. So this is the return address. So you first push the return address into the stack, and then you jump to the destination. Okay, so basically you update the value of RIP. Right, RIP is the PC or program counter or instruction pointer, the same thing, which actually points to the next instruction to execute. Right. So if you execute call instruction, you first push the return address into a stack and update the value of RIP to dest. And then in the next cycle, you're going to start executing the function. Okay? Of course, before you actually execute the call, you actually have to put this argument in the register or stack first, right? You have to do that, because you have to pass some arguments to the function. Return instruction is is kind of opposite. So we actually pop the value. In this case, this value should be the return address from the stack, and use that address for next instruction. Basically, you copy the value into the RIP register, then you can actually come back to the original caller. Right? Other instructions, NOP, opcode is 10. It's a simple 1-byte instruction doing nothing. Just you just skip just one instruction, no operation. And the next instruction is halt. halt is encoded at 0, 0. And if you, whenever you hit upon halt instruction, basically it's like stop the system. So you're just done. Do nothing anymore. Your system stop. Just, it frees your system, and it just stay there forever. Okay. So halt instruction, is like stopping your system, and we actually use this like a halt instruction to stop the simulator, because we run our code in the simulator. So whenever you hit upon like a halt instruction, then we know that your code is finished. Okay, so in that case, from there we can actually start grading your code, because now we can check the value of the registers and so on. Make sure that they are all correctly set, and that actually kind of gives a signal that the code you have written is already finished. Okay, so it's like a halt instruction. And there's like an interesting like encoding decision. So they actually decide to halt instruction to encode the halt instruction with 0, 0. And the reason was, this encoding ensures that the program hitting memory initialized to 0 will halt. So what does it mean? So whenever, let's say you boot up your system, then in many cases, your memories are all initialized to 0. And then somehow you jump to some like uninitialized region of your program, then by mistake, maybe, then it actually immediately halts the system, because generally memory values are initialized to 0. It's kind of for safety. Otherwise, if let's say you jump to some random location, then there may be some like a garbage code. Then maybe they may do something harm to your system. But to prevent that kind of things from happening, so whenever you hit upon the value of opcode of 0, then the system just halt and just stay there to not break your system. And status conditions, if you remember, we actually had this one, stat. What is that? So we didn't really talk much about this. This is called like a program status register. So it's like a global register showing that what's the status of your system. And, so, it actually has, several values in it. So if the code is 1, then this is like A-OK. A-OK means everything is OK. I mean, A-OK is basically everything is OK. You can simply keep going. If code is 2, then we actually hit the halt instruction. So we just stop the system. That's the status of the system. And the third one is if the code is 3, then we actually hit upon bad address, either for instruction or data, because for instruction, maybe you can jump to some undefined memory region, right? And in case of a data, for a load and store instruction, like a move instruction, IR move, RM move, or MR move, like a memory, when you access memory, that address may be ill-defined, meaning it may be out of range, or some bad thing. Anyway, some bad address can happen for both instruction and data. And whenever you hit upon this bad address, this conditional status, the status becomes 3, which is you just hit upon bad address. So in general, if you actually have a real system, and maybe this kind of thing happens, what's going to happen? Do you know? Anyone knows? What happens if you hit upon bad address, or what happens in real program, in real system? What happens? Blue screen. Yeah. One example is blue. Yes. Blue screen, but it's not. It's very poorly handling the error. Generally, if you see, if you have you hit a bad address, usually it gives you some error message, something like a segmentation fault, or a bus error, or the basic mechanism is whenever you hit upon this kind of bad address, the CPU, the hardware, actually traps the operating system. So it actually gives a signal to the operating system. The operating system actually catches this interrupt, and then see what's the reason for this interrupt. And then it shows the right, message or to the right action for the problem. So the correct way to handle this is actually whenever you hit upon like a new like bad address, the OS actually should give you a message like a segmentation fault, bus error, and all these like things, and stop your program. That's the right thing to do. But in some like rare cases, hopefully rare cases, not that rare, but in rare cases of OS cannot handle this case, it actually shows a blue screen. This is actually handled by BIOS and more lower levels software than like operating systems. So, and then 4 is invalid instruction is encountered. Sometimes you actually jump to like a memory location, and then instruction there is undefined, not defined. Maybe something like, if you actually remember, something like, in this case, let's say we don't define anything for like something like C0. Instruction C0 is not defined in this case, right? Because we only define 0, 0 through B0, but there's no instruction defined for C0. So this is an example of like undefined instruction. But let's say your PC goes to some like memory location that actually has value of C0, then actually CPU doesn't know what to do with this instruction. So in that case, it simply stops, and with like this showing that invalid instruction the CPU has encountered the invalid instruction. So desired behavior, if A-OK, like a code is 1, then just keep going, executing the program. Otherwise, if the value is anything other than 1, then you actually have to stop the program and do something. Show error message or something like that. So OS actually should do something. The last topic about in this lecture is about CISC versus like a RISC ISA. So if you, because we already learned what is ISA, right? What ISA defines. So instruction set architecture defines the set of registers and instructions and addressing mode, and so on. All these things are defined as part of ISA, instruction set architecture. And there are two distinct styles of architecture. Which one is called like a CISC architecture and RISC architecture. I think I mentioned this like before. So this one's kind of more like a reiterating of what we covered. But there are two design styles of ISA, like a RISC, CISC, and RISC. This one is, you should understand the difference between, it's kind of common sense for computer science major. So you should understand the difference between the two. The CISC is, it stands for Complex Instruction Set Computer, and x86 architecture is such an example. x86 ISA defines about more than like 1,000 instructions. I mean, a lot of instructions, many instructions, and they also support very complex addressing mode, scaled, indirect, addressing, which is very complex addressing mode, and so there are several features of typical CISC architecture, ISA. They are basically stack-oriented instruction set. Because in CISC architecture, your instruction decoding logic becomes very complex because your hardware becomes very complex because you have many complex instructions. So you have relatively smaller number of registers because you actually spend more silicon hardware for like decoding and supporting like a complex instructions. So as a result, you only have like a relatively lower number of registers. So this is the reason why it's like a stack-oriented instruction set, because you actually put more data into the stack than register. Okay, so that's basically characteristics of CISC architecture. So usually they use stack to pass arguments and save program counter, and there's explicit like push and pop instructions. And also like arithmetic instructions can access memory. This one is very example of very complex addressing mode. Add queue. This one is like a store instruction. Read the value from like memory, and then add RAX register, value of RAX register, and then copy the result back to the memory. It's a very complex instruction, right? Requires memory read and write, and complex address calculation. It's in a sense, in a single instruction, it does load and store in a single instruction plus add, right? But if you actually do the same thing in RISC architecture does not really support like this kind of complex addressing mode. So it only support maybe like a address plus like displacement, you know, like a register plus displacement, something like, you know. So they actually have some like a, if you actually do the same thing in like a RISC architecture, you actually have to first do the load instruction, like a move something. Let's say you copy the value of, you know, no, actually before doing the load, you actually have to do like address calculation first, followed by like load instruction, followed by add instruction, followed by store instruction. If you actually do the same thing in like CISC architecture, RISC architecture, because RISC architecture do not support this kind of very complex addressing mode. So it actually has to first calculate the address using multiple instructions. Basically, you know, add the value of this. You first scale the value of this register by 8, and then add the value to this register. You know, this is address calculation is done by this like part. And now you access the memory using this instruction. I mean, using this address, and you know, copy the value into register and add this value into the register, and then store the result back to the memory. I mean, it takes like at least like 4 or 5 instructions to do the same thing. But you know, in this case, you know, this one can be done. The same thing can be done only using like a single instruction. And conditional code, you know, there are like a flag registers are very common in like a CISC architecture. And philosophy is, you know, add instructions to perform like a typical programming task. So if there's some like a program pattern, then you know there are some instructions that actually captures that pattern. So that's just the philosophy of CISC architecture. So CISC architecture tries to do, you know, like every instructions are more capable. I mean, it's more powerful, more complex instructions, but actually, you know, it actually is more expensive to realize them in hardware. In contrast, the RISC architecture is like a reduced instruction set computer. Stands for actually reduced instruction set computer, and you know, it's actually, you know, RISC architecture is kind of more common. I mean, today, I mean, it's the general philosophy is fewer, simpler instructions to execute them with like a small and fast hardware. So the difference between the two camps is that first camp, CISC, they actually provide more capable instruction, but these instructions are actually slower in execution. But in RISC architecture, you actually have much simpler, you know, instruction, but they can run it much faster. Okay, so. And also, you know, RISC architectures are generally register-oriented instruction set. So generally many more, you know, registers than CISC counterpart. And for example, they actually use like arguments, return pointers, and temporaries for, they actually use registers for arguments, return pointers, and temporaries. But in like a typical CISC architecture, they actually use stack instead of registers. Okay. Only load and store instructions can access memory. This is the reason why RISC architecture is called load store architecture. So load store architecture is, you know, you actually have only load and store instruction can access memory, not arithmetic instruction. Something like in the previous slide, this arithmetic instruction cannot access memory in typical RISC architecture. So that's the reason why they are called like a load store architecture. And no conditional code, you know, they actually use like a general purpose, because they have many registers in general. They can actually use the general purpose register to store this conditional result of test. I mean, the conditional code, instead of using conditional code, you can actually do the same using, you know, general purpose register. So this one actually shows an example of a CISC ISA. So CISC, one of the popular CISC architecture is MIPS, and this is very similar to ARM architecture too. So ARM ISA is pretty similar to MIPS. So, you know, they actually have 32 registers from 0 through 31. So there are 32 registers. And you know, here are some like MIPS instruction, like RISC architecture examples. You know, MIPS is fixed with ISA. So in the previous like x86 64, different instructions actually have different lengths, right? Maybe some instruction took just as small as like 1 byte, and some instruction take as many as like 10 bytes, right? It's like a variable length instruction, right? x86. But in this case, all the instruction actually has fixed size of 32 bytes. Okay, so and then if you actually do some like a register computation, let's say it actually has like a add instruction, register 3, register. This, by the way, in this example, this one is not really constant, but this is like a register 3. Sorry for the confusion in the notation. So in like this $sign, in this example, this one is like a register number 3, and register number 2, and this register number 1. So if you actually you specify 3 registers, then it actually add the value of register 2 and register 1 and store the value to the register 3. Okay, and there are load and store instruction, which actually support this like a displacement addressing. Like if you want to load the value, you load the value from the register value 2 plus like this displacement 16, and you load the value from that location. And for store, you do the opposite. You copy the value of register 3 to the memory location, $2 plus 16. That's the register, the memory location we want to access. Branch instruction, jump instruction, that's pretty much it. Nothing else. So naturally, if you write the same code and compile it, what will be the benefit of CISC architecture? The question number 1 is, if you actually compile the same source code to 2 different architecture, maybe x86 and MIPS or ARM, which which binary is likely to have like a smaller size? CISC가 더 smaller size겠죠. 왜냐하면은 더 적은 수의 명령어로 같은 내용을 표현할 수 있으니까. Because we can represent the same program using fewer instructions. That's the characteristic of CISC, right? So generally, actually, it takes more instruction in RISC, right? Then what's good about the RISC? So here are cons and pros. There are like a big historic debate between CISC camp and RISC camp. So CISC proponents claims that it's actually easy for compiler because it's like more like direct translation from source code to assembly code, because assembly code is very powerful and very complex. So generally, it takes fewer code bytes. Smaller like a size for your executable. Your binary code. The RISC proponents claims that they are actually better for optimizing compiler because now you actually have more simpler instruction. Optimizing compiler can do better job to optimizing your program and but better yet is you can actually make this code run fast with simple chip design, because your instructions are really, really simple in RISC architecture. So you can actually put more resource for something more useful, like adder or like registers. That can do some like a real job instead of like decoding or some like overhead instructions. Some overhead for this like implementing this complex stuff. So current status after long debates. The desktop processors, x86 is clear winner. x86 is CISC architecture, and it's clear winner. Then choice of ISA is not a technical issue, but more about this business issue, because the legacy support, the software compatibility is more important issue for desktops and servers. So with enough hardware, anything you can run basically you can make anything run fast. Either is CISC or RISC. It's not really a technical issue, but more about code compatibility and the legacy support is more important. So x86-64 is adopted, but x86-64 adopted many RISC features such as more registers and use them for argument passing. That's kind of example of like a RISC features adopted by x86-64. But for embedded systems, RISC actually makes more sense because there's like a less overhead. Instructions are very simple. Hardware is very simple, so it's very cost effective, and you can actually it actually consumes less power. That's the reason why most cell phones use ARM processor, which is RISC, but the x86 is doing very poorly in the mobile and like embedded domain. Okay. All right. So I think this is pretty much it for this part. Any questions about the y86-64 ISA? lab hardware homework 2. So how was the homework 2? I saw like about 30 people finished perfect score. 40는? 40명밖에 안 했어요? 남은 16명 지금 뭐 하고 있는 거야 지금? 어디? 아, 쌤 6개씩 끝낸 사람이 44명이라고? 오케이. 난 낸 사람이 44명이라는 줄 알고. 오늘 밤까지죠? Okay, so please submit by tonight, 11:59 Korean Standard Time. Not, don't claim like other time zone. Okay. Oh, by the way, so we're gonna have homework number 3 on Thursday. So we're gonna have give you guys a new homework number 3 on Thursday, but we're gonna give you a little bit more than 2 weeks because we're gonna have midterm, so we're gonna have we're gonna give you like 5 days more than 2 weeks, so that you can actually finish the homework number 3 after the midterm exam. Also, we're gonna post like last year's sample midterm with solutions to help you study. So please, make sure you actually study the last year's material so that you understand the styles and what kind of questions will be asked. All right. So let's move on to more of a hardware side now. So now we defined the set of instructions we want to implement in hardware. So in the rest of the course is about how we can realize real hardware that can execute that set of instructions. Okay, that's what we want to do. So now we switch gear from a software side to the hardware side. So now we're gonna do a lot of this logic gates and AND gate, OR gate, all this hardware stuff. So please stay tuned. Before we do that, let's briefly review the logic design first, because we assume your knowledge on this logic design, but just in case, maybe you just come back from military service or some other reason, your memory for this logic design vaporized, and we want to kind of remind you of how we can do it. So as I said, the processor design is more like making a big finite state machine that can execute, that takes instruction as input and it changes to the next state continuously. Okay, that's basically what this CPU is all about. So it's big FSM, finite state machine. And this part is covered by chapter 4.2. So if you if you understand more in depth, please check out the textbook. And first of all, logic design any kind of logic can be divided into 2 different things. Is either combinational logic or sequential logic, right? Hopefully you understand the difference between the 2. So combinational logic is whenever input in, output out. I mean, just input changes, the output continuously changes. There's no state, no memory in it. So input changes, then output will be changed immediately after a little bit of delay, of course. That's combinational logic, no memory in it. And the second one is sequential logic, which actually has memory in it, like flip-flops, latches, all these things. They actually have memory. So the output in sequential logic is a function of both the current input and the previous, a history of the input. Okay, so that's the difference between combinational and sequential logic. And also, we're going to introduce what is called HCL, Hardware Control Language, which is like a toy hardware description language. This is called Hardware Description Language. So this is toy hardware description language to basically describe a hardware. Okay, so have you ever used any HDL before? If you took the logic design, you probably have used Verilog, right? So Verilog is a de facto standard for HDL, hardware description language, but we're going to use very simple C-like, toy hardware description language, in this course to specify, this design of the hardware. That's a topic. So, I'm going to move this part very quickly. So, I assume this one is a review. So, fundamentals or hardware requirements. If you want to design any hardware, there are several components. It requires communication, computation, and storage. So, for communication, you actually have to somehow you have to move value of your hardware to another location. Usually, it's achieved by wires, right? If you have like wires, then you can just put some data value from one location to another, using communication channel. And also computation and storage. Computation is to actually do something useful, maybe to add, multiply, and all these things. You actually do some like transform input data to something else. That's computation. And storage is memory. You put your data in this like storage element. And bits are our friend. Everything is represented in bits. They actually, everything is expressed in sequence of ones and zeros. So that's bits are basic most fundamental element in our logic design. So communication, you actually we actually use voltage level, low voltage or high voltage on wire to specify ones and zero. And for computation, we actually compute like a Boolean functions using like bits, and storage, we store bits of information using flip-flops and latches and so on. Okay, hopefully, all of these like phrases or all these things actually you're familiar with all these concepts. So let's start with how we can represent a value of 1 and 0. So we use physically we use a voltage level to specify ones and 0. So if it's like a high voltage is 1, if low voltage is 0. So use like a voltage threshold to extract like discrete value from continuous signal. So if your voltage level is somewhere in this like a yellow region, this one is interpreted as 0, and this one is if your voltage level is somewhere in this like an upper like a yellow region, then this one will be interpreted as like 1, and this one is basically forbidden region. So we are not using like this region because this one is kind of margin between ones and 0. Because sometimes if you actually use like this value, of course this one looks a little bit closer to 1, but it's still very close to 0 too. So we want to have some margin to work reliably. So it's either high range or low range. High range is 1, low range is 0, and there's like guard. Forbidden region, this one is also called guard between them. So the good thing about this, like using this digital signal, is it's actually very tolerant to errors, noise. So let's say you store some value 1 here, and let's say there's some like a thunderstorm, and so maybe this one fluctuates a little bit, but still the value is still maintained, right? So in this way, we can actually, regenerate the value of 1 and clean 0, even with some like a noise in the environment. So here are like let's move on to computing. How we can compute the value? Most fundamental logic gates are AND, OR, and NOT, right? So out is in this case the AND gate. It actually the output becomes 1. If and only if both inputs are 1. In case of OR, output becomes 1 if either of the two or both values are 1. And NOT is simply the negating the value. If 1 is 0, output, then the input is 1, output will be 0. Input is 0, then output will be 1. And the output responds continuously to the change in inputs. Of course, with a little bit of delay. So if you see, this example waveform. So let's say initially there are two signals, A and B. So let's say this green is B and red is A. So initially the value of B is 1 and value of A is 0, right? So if it's AND gate, the output will be this like a solid line. So the output, this one will be 0, right? But input actually changes, but eventually at this point, both inputs actually becomes 1, right? Then the output becomes also 1 after a little bit of delay. Because both inputs are 1, at this point, both inputs are 1, so the output should be 1, but after a little bit of delay, and this is called rising delay because the delay for the value make a transition from 0 to 1 is a rising delay. And let's say after a little while, this A signal becomes 0 again. Then now value is 0 and 1, so the output should be 0. Then again after a little bit of delay, this is called falling delay. The output becomes 0 again. Right? That's basically how this circuit works. This is basically combinational logic because the output respond continuously. There's no state. So output is a pure function of the input. Okay? So if you generalize it, you can actually think of an acyclic network of logic gates. So any combinational logic can be realized as network of gates, right? Network of combinational logic, like AND or NOT, right? So there are set of inputs and set of outputs, and the outputs continuously respond to change in the primary inputs, and output actually becomes the Boolean function. It can be described as Boolean function of some input. Okay. Of course, after a little bit of delay. So the beauty of using like Boolean algebra is any combinational logic. I mean, this in general, like digital logic, can be represented as a simple like a Boolean function, right? So there's a one-to-one correspondence between this mathematical model, which is Boolean function, and physical like a network of gates. So they actually like nice like a one-to-one correspondence. So let's take a look at a few examples of how we can implement some like interesting components using combination logic. So first one we want to look at is bit equality. So what this bit equality does is it takes 2 bits as input, A and B, and generates output, EQ as output. So what it does is it generates the output 1 if and only if both A and B are equal. So if you write the truth table for this function, let's say A, B, EQ, then there will be 4 different combinations, 0, 0, 0, 1, 1, 0, 1, 1. The output will be 1 in these 2 cases. In the other cases, this one is 0. Can anyone recall what is this function? What is this function called? XNOR. X, not XOR, XNOR, right? Not XOR. So this is called XNOR. So that's the reason why XNOR is also called equality function. If they are equal, then output is 1. Otherwise, they are 0. And we also introduced a very simple hardware description language called HCL, hardware control language. This one actually represents this Boolean relationship between input and output using this expression, bool. So this one means the output type EQ is Boolean type, like Boolean is a 1-bit information. Boolean type EQ is defined as A and B, or not A and not B. This one is very similar to C like representation, right? So this one actually shows that the output EQ is true if both A and B are 1, or both A and B are 0. Okay, so this one is basically a very handy way to represent this functionality using C-like syntax, and this is called HCL, hardware control language. This one is not. This is not really anything like industry standard or anything like that. It's just simply, this is defined in this textbook. I mean, it's simple like toy language. So to represent this functionality. So we're going to use this like a HCL, hardware control language, to describe control logic for processors. We can actually expand this bit equality to word equality. So now we can replicate this bit equality 64 times, and then gather all these output signal into the single like an AND gate. So this one is like 64 input AND gate. Huge like an AND gate. So what it does is it compare like a 2 word value, 2 like 64-bit words, and if both are equal, then the output becomes 1. Otherwise, the output will be 0. Okay, so to realize that, we can actually use like a 64 copies of a bit equality, like bit comparator, and then take all the outputs into the input of the AND gate. That's it. So this one is the pictorial like representation. It takes 2 words and generates 1 bit output. By the way, this like a solid line. This solid line shows the word signal, and this dotted line shows a bit signal, the single bit. So this one is like this one is a word. This one is like a bit. Okay. So if you see this like representation, you know that it takes 2 words as input, and it generates like a single bit output. And in HCL representation, again, the output type is Boolean. Output type is like a general, simple like a 1 bit like output is true if and only if both A and B are the same. Okay. That's like a word equality. What about multiplexer? So if you remember, maybe if you've taken this logic design, you remember this one. So it actually has like 2 inputs, A and B, and there's a selection signal, and there's output like this, right? So if this one has different conventions. So if this one is 0, 1, like this. So if the selection signal is 1, then A goes out. If selection signal is 0, then B goes out. Okay, it's like a selection selector. So in HCL expression, the Boolean output will be S and A, or not S and B. So you can actually prove this one actually is true. For example, if S equals 0, let's say selection signal is 0, then this one will go away, right? Because as is 0, anything you take n to 0 will be 0, and this one will become 1, and only it will remain. If S is 0, the output will be B, right? If S equals 1, again, you can actually plug in this value into the expression here, then the output will be A. So we know that this one is actually true. I mean, faithfully describing this multiplexer. We can expand it to like a word multiplexer, like again, in the same way. If the block diagram looks like this, it takes 2 words as input, A and B, and takes 1 bit like a selection signal. And if the value is 0, then the output, word B will go out. If it's 1, then word A will go out. Okay. In HCL representation, we actually use this format. So in this case, the output is integer, like a word, like a generally it's like an integer. So the output is word, and it's like a switch case statement. If you understand the C language, switch case. So if this condition is satisfied, then the output value will be this one. Otherwise, we move on to next line. So if it's true, then the output will be on the right side, something like that. So this one, in this representation, is like either you can think of it as like a switch case statement, or more of it's like an if chain. So you actually do it's something like you can translate like this part is something like if S is true, then the output is A, and else if then output is B, and so on. Or you can think of it like a return or return. Okay? So that's basically what this expression describes. How you can parse this like expression. You first check the condition of this thing, S. If this one is true, then output will be A. If not, you move on to the next line. And if it's true, then actually this one will be the value. So again, we actually can prove this, whether this one is correctly implementing this like a multiplexer. So if S equals 1, then the first line will become true, right? So the output value will be 1. If S equals 0, then the first line will become false, right? So now we move on to the second line. And the second line is always true, right? Because the condition is 1, right? That's always true. So the output will be B. Okay, so output value for the first successful test in sequence, in this case. And HCL for word level, like a few more like a word level examples. The first one is minimum of 3 words. It takes like 3 words, A, B, and C as input, and it selects the minimum of the 3 as output. It's another like combination logic, right? So if you want to describe that, so like output min3 is defined as follows. The first one, if A is less than and A is less than B and C, then actually the output will be A, right? If this one is satisfied. If it's not satisfied, now we move on to second like line. And in this case, if B is less than A and B is less than C, if both are satisfied, then the output should be B. If none of the above, the output will be C. Okay, so that's basically how we can describe this logic in HCL, the hardware control language. The next example is a 4-way multiplexer. So in this case, according to the block diagram, we take 4 inputs, D0 through D3, like 4 input words, and we have 2-bit like a selection signal, S0 and S1. So in this case, the output 4 is defined as you first check whether both S1 and S0 are zeros, right? So if this one is satisfied, implying that both S1 and S1 are zeros, then the output will be D0. If S1 is not 0, then what will be the S0 in this case? In the second case, what will be the S0 in this case? S0의 값은 뭘까요, 여기서는? 두 번째 케이스에는. Because we already failed the first test, because in the first test, we checked whether both S0 and S1 are zeros, right? Actually, we failed. That implies that if S1 is not true, then S0 will be always 1, right? Because if S0 were 0, we actually would have passed, we would actually, this condition would have been satisfied. But we are in the second line. That means this condition is not satisfied. So we know that S0 will be already 1. So now we can if this one is we can only check like this condition, because we don't have to check the condition for S0. And in the third case, we also check the not S0. So if it's not S0, then we actually pass out the 2. Likewise, we know that this one will be this one will be already S1, because if it's not 0, we already have a hit. We would have hit like this first condition, right? And the final output will be the last one will be D3. All right. So I think I was before I stop. A하고 B가 같은 경우에는 어떻게 될까요? A하고 B가 같으면 어떻게 되죠? 그렇게 되나? A하고 B가 같은데 C는 B보다 크고. 그러니까 예를 들어서 4, 4, 6. 그런 경우에는 원래 4가 나가야 되는데 진짜 4가 나가는지 볼까? A하고 B는 true, false 문제가 있네. 6이 나가겠네요. 그러면 잘못. 이렇게 해야 되나? 이렇게 하면 픽스 되죠? 네. 굿 포인트. 고맙습니다. 맞네요. 그 말이 맞죠? 4, 4, 6 예를 보면 이렇게 하는 게 맞죠? 네. 고치세요. 네. 네, 하여튼 여기까지. 숙제 안 내신 분들은 다 오늘 밤까지